Yeah, this is asymmetric, sine 0. Sine 0, yes. I have one side and the other side, which is, yeah, no. Up to you, okay, something. You won't block the view at all from the video notes, so not a problem. Okay, so the sine 0 is necessary actually because we distinguish negative infinity from infinity. Okay, so sine 0 is represented for sure when your exponent and matissa are both 0, but the sign field is 0 or 1. Okay, so we do have a negative 0, okay, and a positive 0. Okay, this is something that's supported, but we also dictate that they are equal. If you test the negative 0 and positive 0, they are equal. Okay, this is not true. Okay, for sure in your platform you should test it. Okay, see whether a sine 0 is supported, or when they are supported, when the positive 0 and the negative 0 are they equal. Okay, since we distinguish these two, okay, you imagine this should be always true, right? The inverse of the inverse functions should always be self. Okay, but if you say when x is infinite, okay, or negative infinite, okay, if you don't distinguish between the two zeros, and this will be 1 over 0, this is negative infinite, say x is negative infinite, and you'd have no distinction of positive 0 and negative 0, these may not be equal, right? Because this can be negative infinite, this is infinite. So if you distinguish infinite and negative infinite, then it is good that you distinguish the positive 0 and negative 0. But when they are directly compared, they're actually equal. We just reserve different signs for their representation. Okay. Another example that you distinguish the negative and the positive 0 is when you implement a log function. When log is positive 0, the definition should be negative infinity. But when x is negative 0 in log, then it should be not a number, right? Just strictly from the asymptotic behavior of a log function, right? Whatever function carries a discontinuity at 0, then this is necessary, right? Because 0 has a discontinuity, positive 0 is semi-defined, but negative 0 is not a number. Okay, so the sine 0 it's supported in most of the IEEE 754 standard. Okay, feel free to see it on the other side as well. Okay, yes.
So will the sine 0 only existing in the floating type?
Yes, only in floating point.
So if, for example, if we have an integer type, if I assign it to like positive 0 and negative 0, it's always be 0. There's no influence on that, right?
For integer or floating point?
For integer.
Integer, there's no difference. Okay. Integer, actually, there's no distinction. There's no reserved symbols for positive or negative 0.
Okay.
If your platform choose to do so, it's possible, okay? But it's not the IEEE standard.
Okay.
Okay. Maybe worth a test, okay? That's the, if you have infinite, if you distinguish infinite and negative infinite, then there's a reason to distinguish positive 0 and negative 0 to preserve the double inverse function to be itself. Okay, so there's a reason to do it, right? But if integers, many of the integers, they don't support even overflow, there's no idea what is called infinite in integers, then there's less reason to implement something called positive 0 or negative 0 in integers. Okay? Okay. So let's try it, okay? Let's try this positive 0 and negative 0 on your platform, okay? We are going to write a small function to test this, okay? But let's make sure when you generate a function, I would like you write a function called is positive 0, okay? And that will only return true when the representation is a positive 0 floating point. Okay, let me say, okay, I want you to write a function where when the argument passed in is the positive 0, then that's the only place that it will return true. Okay, any of the other, right? Say 1, -1, all these double max or -0, infinite, pass in, they should all be false. Okay, so this is not as simple as equal to 0, right? If you test equal to 0, in most of the scheme, it will return you just say, okay, even negative true, -0 is equal to +0. Okay, so let's figure out, okay, a small function called is +0. And I would like you to pass in all this to test your functions. Okay, and this should be, in C, should be like 3 lines of code. Okay, generation of those special case is something that takes a little bit more lines, but the function should be only 2 or 3 lines. Okay, let's use your computer to see how if you can write this is +0 function. Okay. Probably the hint is that you have to go from the inverse, right? The inverse of that parameter has to be positive infinite, right? So you cannot test it's equal 0 directly because +0 is equal to -0. Okay, you have to test the inverse of that parameter to see whether the only return. Okay, I want this function. Okay, write this function. A Boolean function return true only with +0. Okay. That's right. And from that implementation, you probably will know whether your platform even support +0 or -0 for sure. Okay. And this code will be useful because it's part of your code assignment 1. Right. Feel free to do in Python or C or MATLAB, Java. Okay. Feel free to raise questions as well, okay? Saying that you get a weird, strange result, okay? Please report your strange results. Yes?
Are we supposed to just compare it with like positives? I'm not exactly sure.
Let me see. Where is your statement? Oh, okay, sorry. Okay. If you just write if x is equal to +0, you are not sure whether that +0 is even a supported semantics. right? Because in the semantics, this is PowerPoint, right? Not Python, right? So you need to generate your positive 0 from infinity, 1 over infinity, right? Negative 0 is 1 over negative infinity, right? So the first you have to generate infinity, right? So if you just saying that x equal to positive 0, then you are not asking the implementation, okay? If you have a statement like this, okay, then this is really, you're testing the semantics of your language, not how it's implemented, right? So what you should do is that, in the private part, right, generate something that's infinite, y, okay. Again, this is usually not supported. Okay, semantics is not supported, right? You need to generate the infinite from, say, double max times 2, say, to 10 to the 1,000, okay? Whether you generate an infinite, okay? And you assign your x, right? And then the y is equals to 1 over y, right? And then you ask whether your x is equal to y. Got it?
I think so.
If do you test the negative 0?
Yeah.
Okay, but the function don't return true when passing. Okay. So and what platform you have?
C++.
C++. Okay, C++ on Linux. Yeah, please do. You have one person want to see how you implement it. Yes, you got it too?
Yeah, Python on.
Python supported, Python floating point actually support the IEEE 754 standards, okay? Their integers are infinite precisions, as we find out last time. It's just according to its memory, okay? So the integer is not IEEE standard, but they use infinite precision for integers, okay? But the floating point, Python, actually I look it up, Python supported IEEE 754 exactly, okay?
I'm just
Yes?
testing it out.
You also got it, okay? So this is a practice. If you cannot somehow generate it, okay, leave this for your code assignment 1. Okay, this is something that's the helpful, okay, okay. Okay. Now, and this hacker practice is, as I mentioned, this is something that if you go for a programmer interview, you need to get used to it, okay? Many students don't get used to writing program immediately, okay? I hope that this class will help overcome that fear, okay? When in doubt, write a small program, know how to test it. It's, one of the great capabilities you can have as a competent programmer, okay? Okay, now let's think about what is underflow, okay? Underflow is something will happen in many calculations, okay? Typically it's whether underflow, right? Underflow, if underflow happen and you don't handle it, then when x minus y is equal 0, when x is not equal to y. We give that example, right? So x minus y equal to 0 simply because you don't have enough precision to record it. So it becomes 0. But x actually is not equal to y if you don't do underflow, okay? So underflow in IEEE format is handling this, okay? So it tests how small is the number, okay? How small, check the exponent field. When exponent field is less than a critical bias, then the presentations is changed from 1 point f to 0 point f, okay? You see, do I document it here? Okay, yes, here, okay? So when E is checked, okay, when it's larger, then it's this behavior, these representations. When the exponent is less than the minimal exponent that you can have, then the mantissa means the 0 times this. Okay, let's see how this is implemented, right? So when in this exponent, mantissa is always larger than 1, right? Because that's how your scientific representation is, right? When you write something that's to the power, e to the power of something, it means the mantissa is 1 point something, right? And that also means the mantissa is always larger than 1, right? When you want to represent a small number, even below what is allowed in the E field, you have to switch to 0 point something, right? Because this 0.001 is smaller than 1. It lost precision, but it is smaller than 1. So you can represent a smaller number, right, within the given precision. Okay, so every floating point, you check whether your exponent is larger or equal to this minimal minus 1, okay, which is nothing but, okay, in the binary, okay, it's something like the 2 to the minus 10220, okay, like this, okay. And once this is done, okay, then the representation change, okay, so that it's going for this, okay. So you can represent an even smaller number. And when it all becomes, even the mantissa becomes 0, you can see all of a sudden now it is continuous. Before, if you only have this representation, as your mantissa is always larger than 1. Okay? When that smallest point go to 0, go to your positive 0, it is discontinuity in your precision, right? Now when you implement this, you gradually become positive 0. There's no more discontinuity in the sense of your floating point representation. Okay, so if you implement this, then this is always true. Okay, you handle, it's not that I have infinite precision now, but if I handle using a switch in this mantissa representation, then you can prove that when x equal to y, x minus y equal to 0, and only if x minus y equal to 0. Okay. So this is why the underflow is handled, okay, to preserve this equivalency, okay. So that so let's try it, okay. This is, I know, is rather unreal, okay, on these things. Let's try it, okay. So now I give you a double that's of 16 significant digit. Okay, so this is this strange number. I just want you to have a number that's represented with 16 digit. Okay. Now when you have, okay, the normal, okay, so let's create some very small number, okay, very small number. You times this precision, give a very small exponent, so that you approach that E minimal faster, okay. And let's divide it by 10, okay, and then compare x, okay. If your program execute the gradual 0, okay, or the gradual underflow, then you should see that the printout is going to be, first is this one, e to the minus 307, okay. And when it becomes 308, 309, okay, things, and you will simultaneously see the loss in your precision. Let's see if this works, okay, in your standard, which is surprising, but it is actually there for a good purpose, okay, for underflow control. Okay, so you can use an equivalent Python to implement this, or just this is a sample C code. Okay, let's see how your platform perform. Okay. In this example, actually, you'll appreciate how Python can be faster in programming than C. Right? There's no declaration things. You just have to type in the assignment, in the for loop, you're done. Eh? One, two. Can you extend the precision of your print? Or the Python, do you have that control?
I have not come across it.
Okay.
I'll check.
Okay. Sure. So this is loss of precisions by Python. Okay, but in order to see the full precision, you need to ask the program to print out the entire precision. Okay, I forgot what is the default in the C++. They only print out like the last 8 digit. Yeah, something like this. But you have to extend it. Print is called printf E16.3 or something. Yeah, I forgot. Okay. Yeah. So you have to, in order to see the gradual all the way, but you can see that when it is within the 9 precision, then you should gradually lose precision.
I think I'm still losing position. I don't even have that. I don't even have the entire, all of it being displayed. I can just see from the first 10 decimal point that it's not.
Really?
I don't know if I'm doing something wrong, but this is not right at all. That's my double. I multiply it, and then 20
multiply divided by 10, C out. So you didn't say anything. What is the execution? This one?
I'm just printing out X.
Yeah, but isn't X should be 1 point something?
Yeah.
This is a printout?
Yeah. I can recompile.
Okay, there is something wrong. What?
The same result.
Same result.
Yes.
So mine start with some 3 point something.
Yeah.
Interesting. Okay.
Negative.
-3. Okay. So your platform is not IEEE 754 compliant. If that's a case, right? If you are within the allow smallest number to be represented, right? When you gradually decrease it, you should observe gradual underflow. Right? But if that's not the case, then check mark. Whenever an important calculation involving 2 large numbers, you need to implement the underflow yourself if your platform don't support it correctly. Okay. I'm not exactly sure whether this need to be debugged for that. Okay. Okay. Yes.
I'm not sure what it is supposed to communicate here. This is the result if I display it. It's different from the result if I display it in the variable format, which is this is
because when you display, you need to display with
rounded off.
rounding off, right? So, but you can see you lose precision when you round off, right?
Yeah.
So this is what? This is MATLAB?
Yes.
Okay. So MATLAB is handling the underflow gradually. You can see that, okay? But you somehow have to figure out how when you print out a floating point, print out more precision, more than this, yeah. So the default for your program in MATLAB is 5 significant digit. In here is only 4 significant digit, and then they do round off, right?
When I
So,
try to increase the precision, it just gives me only 0.
what?
When I increase the precision, I get all zeros.
Is that this print is not right? So because you only print out something that's in the exponent, I think. Okay, is that .15f is the way you okay. I haven't done this for quite a while for the exact printing. Okay, so .15f in C, I don't forget in Python, means I only do the floating point without the exponent. So because you have such a small number, So it is 0. Supposedly in this format, it will be 0.300 and then have precision, right? For sure, you are printing out the first 15 zeros. That's your dot 15F means. Okay.
If I increase the precision, it just gets random numbers from somewhere.
Get random numbers. Okay. Yes. Yeah, this makes sense. Yeah, this is just you don't show enough digits, right, when you print out. So you can see that it's gradually losing when this is getting smaller. You're gradually losing precision, right? Although you're losing precision right at these 322 to 3333, okay? You're missing one number. Oh, well, no, because this jump. So you lose that precision very fast. It's a binary precision to decimal precision. But you observe that you lose precisions when the number getting smaller before you hit 0. Okay, gradual underflow is you lose your precision gradually before you hit the positive 0. Okay. Yes.
Yeah, increase the precision.
Okay.
But then it's still like.
It's still like very funny.
Yeah, it's so. I think it's under. So I just multiplying by 10 to the negative 307
Okay.
gives me negative 386. Just that. So I have double X. I print it out, which is 1.234, whatever that.
Okay.
And then I just multiply it by 10 to the negative 307. I print it out, and then it's negative 386.
I think that is this expression in C++. That's not correct then. The C++ don't support. I think it's double star, right? It's not. Sorry, this is pseudocode, okay? Yes.
I'm getting zeros, like all zeros. So initially, I initialize my x to this value, and I get this. And ever since, like, I raise it to 307, all the values are 0.
Is just what as I discussed with her, that because this format, 0.220F, means you want to print out in the format 0 point something without the exponent.
Right.
So since your number is 0.300 zeros,
So we
and
won't get anything.
so I think it's called 20E. Let me, I hope I'm correct on my memory for the, so now it's not, right?
Yeah.
So it's not point, in C, it's not 0.20F, meaning printing in the floating point without exponent.
Okay.
0.20E, print out the exponent. So now is you see, right?
Now I understand.
Right. Yeah. It's just a format, okay? So this is a great exercise in this, right? What is syntax and what is the representation? Okay, so sometimes, yes, can be, yeah.
The last 4 values are coming out as 0.
Yes.
Why would that be?
But you do, because now you hit, right? The gradually 0, you hit the positive 0,
Okay, so
that can be handled. But before that, you can see you lost precision.
So this is the least precision that it can have.
Yes,
Okay.
yes. Okay. Take a little bit trial, but it should work, okay? Something that, and as I mentioned many times, okay, in your computation, this happens. X minus y, when both x and y are very large, how do you handle that precision, okay? That happens pretty often, okay? So now you get the first experience, okay, to seeing the underflow. Okay, I'll leave your further explorations, okay, for later. I do have very unusually 15 more minutes that I can, but the last lecture is extra long. So let me cover the last lecture a little bit, okay? Hopefully, the last assignment, like the hacker experience, make your write the first assignment easier. Okay, that's what I want. I want you to observe how your platform be able to handle all these rules. Okay, write a utility, right? When you want to write anything serious on your platform, you need to know. Okay, you need to know how the precisions and exceptions being handled. Okay, and sometimes there are surprises. Okay, either most of the platforms saying they're IEEE 754 compliant. Is that true? Okay, write a utility to test it. Okay, that's your first assignment. Okay. Okay, now we're going to the next important topic. Okay, in your syllabus, I estimate how fast I can go into this, but many of the key concepts, okay, in this class will be shown in this local analysis. Okay, you must have seen the local analysis more than 10 times. Okay, to get a derivative, you use finite difference to get a derivative. Okay. You probably have programmed it with something. But if I ask you the question, okay, when you do a local analysis, whether it's interpolation or extrapolation by finite difference or something, how do you know your computation is correct? Okay, the fundamentals I believe you know already. Okay, you may have done it 10 times. Okay, that you can swear to me that this is the slope. Okay, you may saying that I know the topic, so I don't have to come for the next 5 lectures. Okay, say this is something I know. Okay, but if I ask you the next questions, okay, why do you know what you compute is correct? You know this formula for a long time. Okay, but the next question is more important. Okay, is how do I know my choice of edge is good enough? How do I know that in this function the implementation is correct? Okay, so let's learn that. Okay, so these will carry, and the information, once you understand local analysis, a lot of the principles in the nonlinear solvers, in the ordinary differential equations, okay, then will become more and more clear. Okay, so this is an important topic that we'll go through. Okay, so this is something that it happens in so many applications. Okay, so approximation in local analysis. Many times that we do not know the global behavior of a phenomenon, whether stock market, your emotion, or I have a few sampling point. Okay, most of the time it's in the history. Okay, in the history, now you're interested to know what is behind. Okay, or equivalently, in a physical world, I know the temperature between this point and that point because you have sensors. Okay, but what is in between? Okay, when you do a interpolation, how do you know how good is the interpolation? Okay, it's the subject of this. Okay, something that it goes both with your computational knowledge and somehow your software knowledge as well, right? Because in here you can see a very simple thing. You just tried it. When h is very small, this unavoidably become large number minus large number, and your precision matter, right? So what is left as the precision of the difference of two large numbers actually matters a lot in your local analysis. Okay, so this is just the reality though. Most of the time, for many things, we know a few sampling point. Okay, we know the physical rules. Okay, but now I would like to make predictions. I would like to make interpolations. I would like to make something from my limited knowledge of the function, but to be able to operate on it and still have a way to verify I know what kind of error I'm dealing with. Okay, this will be topic. Okay, so the easiest one is just a Taylor series. Okay, so it's Taylor series. So we say that an approximation is true when h approaches to 0. Okay, so for this is the things I'm using as example. I know that this is what I call as a consistent estimation of the slope, right? When I use this function. Okay, very simple. Okay, that I can prove this easily from the Taylor series for most functions. That I can prove that this is consistent. For sure, if the x is falling on a discontinuous point, then I can prove that this is not true. Right. So this is that you have learned in your calculus or something, that if you want to estimate a slope, right, as long as it is a well-behaved function, okay, then the function, this expression is consistent. If it's not, then it's not consistent, okay? You probably have learned the second order things as well, just from the Taylor expansion, okay, which is not strange, okay? Not strange that if you do the both sides with the same h, then magically you get second order accuracy, okay? You can prove that easily just by writing down the Taylor series expansion for these two. Okay, write down their Taylor expansions, and you will know that you can prove this one readily. Okay, I hope that this is something. If you don't know it, okay, please practice. Okay, fx is equals to fx plus f plum x times x plus h squared. Right. This is just simple Taylor expansion you should have seen many times. Okay, many times. Okay. Just by that simple function, okay, from what you learn as underflow, you will know that your approximation will have something like this. Okay. Okay. Let me go for the two ends. Okay, with you. Your approximation is getting better and better. The y-axis is the relative error. Okay, relative error with the ground truth. Okay, ground truth. If you know the ground truth, okay, for sure, most of the realistic problem you don't know the ground truth. Then what do you do? Okay, so we'll go for examples where ground truth is known to see the method. Okay, and then we'll extend when I don't know the ground truth. What should I do? Okay, what should I do? Okay. So, but you know the behavior is like this, even for the simple expression like this, okay? Simple expression like this. Your approximation getting better when you get a smaller h, because the error is on the order of h squared, right? So this is understandable, okay? This is understandable, right? Because when these two numbers getting too close, you're losing precision. When you lose precisions, the error become bigger, right? So it's the function is just like this, right? Some hesitation on your face. Let's try it. Write a very fast program to use a function that you actually know as fx equal to x squared. So the ground truth is known. Okay, it's a very simple quadratic functions. I'm interested to know how do I estimate the slope at x equal to y. Okay, I know the ground truth, it should be 2. Right, there's really nothing around it, okay, because it's such a simple function I know. Use this function to estimate this one, see how close it is to 2. Okay, decrease your h from 0.1 to 10 to the minus 18. Let's see what is the error of your estimation from this to the ground truth. Okay, simple. Try it. Try it and keep it, okay? Because this will be used as illustrations for many of the things we're going to introduce. If you have no time to make the XY plot, at least tabulate it to see your error decreasing when h, this is log h, okay, decreasing, and then when you see that the error comes up again, okay. When h is 0.1, right, so become 0.01, the answer should improve, right, because your h gets smaller, the approximation getting better. Okay, at this end, 10 to the minus 18, because it is 1 plus 10 to the minus 18, it doesn't handle so much precision. It's 1.0000017 and then 1, right? And that mantissa is not handled well. Okay, so you will get something that's like a lot of errors. Okay. If you find something weird, feel free to voice, because other people may encounter the same problem. Do you get something strange?
That's what is OH.
Oh, no OH. I'm sorry. Eliminated that. The derivative is approximated by the first term.
Okay.
I'm just saying that is the order of h. Okay, the error is on the order of h. When h getting smaller, the approximation getting better.
Okay.
So there's no OH
Okay.
in your program. This is called a big O. OH. This is called a big O. Means on the order of h. When h become half time smaller, the error is half time smaller. Okay. When order h square. When h get half smaller, it become a quarter smaller. Okay, so we call the big O. Okay, big O. Okay, in the automata. Okay. Sorry for that. I should delete that order h here.
I'm trying.
Okay, this actually worth spending some time. Okay, maybe at the close to the end of class, we cannot finish today. Okay, when you have time, do finish this. Okay, I want you to observe that. Okay, and you are so surprised if you change your fx to this function. Okay, where the derivative should be identical. Right? If you switch your fx to be x squared plus 10 to the 8th, you will swear to yourself that the derivative is the same, right? Okay, but if you implement this, you will find something surprising. Okay. Because now your function evaluations has a precision issues, right? You force it to not to be to calculate 10 to the 8th. And later on, if you try this approximation, there'll be even one more surprising thing comes, that there is absolutely no error. However you do it, if you use this approximation, there's absolutely no error. But I want you to see it, okay? Yes, you see that curve. Okay, great.
I just printed the values.
Okay, print out the value. So you decrease and then increase again. Okay, so and the first part is because what we call the truncation error. Okay, I truncate the expressions, right? All the higher order of Taylor expansions is truncated. So it carries the error. Okay, and the error getting smaller when you decrease the h. But then you are limited by the precision of your computation. Okay. Can just you, okay, can you try the second function? It should be one line. Can you see that how does it shift the choice of h to give you the minimal error? Can you try it?
For x equal to 1.
What? This function. Originally is this function, right?
Yeah, for x equal to 1.
Yes, still evaluate at x equal to 1. Yes. Everything is the same. It's just, and you know, your calculus 101 should tell you my answer should be identical, right? I'm doing a derivative of parallel shift. How can it be different? Okay. But you should see the difference. Okay. Yes.
So in my case, this f function of x plus h minus function of x divided by h is coming out like this. So it starts with 2, then it sort of stays around 2, 1.9, 1.9, and then it goes to 2.2.
And why is that?
Not sure.
Because it loses precision, right?
But
Right.
there's no like smooth transition.
When you lose your precision, right, it's something like that can happen, right? Lose precision means I approximate something that's inexact,
Okay.
right? It can oscillate, right? It's just,
Okay.
yeah.
For the second one, I'm getting values as this.
Okay, so it's more errors, right?
Yeah.
Earlier, and that's precisely coming from the precision, right? When you evaluate fxh originally in x squared, you carry the significant digit to this number, right? But if I force this one to be plus 8, I force it, yeah, right. So you will see the round of error, okay? The precision error comes in a lot earlier when I just force it to add a large number, right? And 10 to the 8 is not that large anyway, right? You can imagine this is not bizarre. When I ask you to try problems with 10 to the 307, maybe deep in your heart, say, this never will happen. These are astronomical numbers. No. So why do I need to learn this topic, okay? Now I think you should feel better, you know, just 10 to the 8th, okay? I changed the behavior of such a simple estimation, right? Okay, if you haven't finished, okay, it'll be a good small take home, okay? But do take it home and on Friday lectures, okay, finish this, okay? Finish with your program. There's many important observations I would like to go with you, okay? And give you a encouragement to finish, okay? These will tell you eventually how do you control your error. Just from this very, very simple example, okay? I want to give you your first taste of something called HP adaptivity, okay? How do you use fine resolution to get accuracy, or how do you use higher order to get accuracy when the ground truth is not known? Okay, this will lead to that, okay? And you will see many, many variations of that in the different physical laws, okay? But this will give you the first taste about that adaptivity. An error estimation when the ground truth is not known. Okay, here the ground truth is known, okay, so you can easily check, okay? But when the ground truth is not known, how will you be able to do your error estimation, okay? Will be illustrated by this example, okay? So you please implement it, okay? And it's fully running, okay, for you when you come to the Friday class, and then we can use that to give you the intuitive answer that's very critical for verification of a computation. when the ground truth is not known. Okay? Yes. And you're free to go. Yeah.
It's
Yeah.
got it. So that's what I got. But it starts when I use h as 0.1. I get slope as 2.1.
That's not accurate, right?
Yeah.
Yeah.
but
Yeah. That's because your h is too large, right?
what's 0.1 is too large?
Yeah.
Oh.
Relatively, right? You give a 10% perturbations, try to get a local slope. That perturbation is too large. So when you choose a large perturbation and evaluate the local slope, you get a 2.1, 10% error,
Oh, okay.
right? But then you gradually improve, right?
Yeah.
Until it gets strange,
Yeah.
when the precision is lost.
Well, but what's up with the zeros though?
It's just that this is large, this is so close to this that cannot be handled by the precision, right? They become 0, right?
Yeah.
Your slope should be 2. But when the precision is lost, it becomes 0,
Right.
right? First hand.